Hello everyone, and welcome to today's tutorial. In this session, we will explore the fundamental principles and advanced techniques of signal extraction in pulse oximetry. We'll discuss how this technology differs from conventional measurement methods and discuss the innovations that enable accurate and reliable readings, even in challenging clinical conditions. Conventional pulse oximetry determines arterial oxygen saturation and pulse rate by using theoretical model which was developed over 25 years ago. This model assumes that arterial blood is the only light-absorbing pulsatile components in the optical path. The ratio of pulsatile transmitted red to infrared light. The optical density ratio is used to calculate SpO2 through the use of a calibration equation generated by human in vivo calibration studies. Limitations of conventional pulse oximetry. Continuous and accurate measurements of SpO2 is difficult in the clinical environment. Excessive ambient light and electromagnetic interference may disrupt the measurements completely. Poor tissue perfusion may produce signal strength below the limit of detection, and this condition may be exacerbated in patients with dark pigmentation. The effects of motion on pulse oximetry accuracy may be more insidious than causing complete failure to measure SpO2 or pulse rate dropout. How to measure accurate saturation measurements during motion. During motion, venous blood and other non-arterial absorptive substances generate pulsatile optical signals as they move and attenuate the transmitted light. During motion, these non-arterial saturation components contributes their own pulsatile signal which cannot be separated from the arterial signal by conventional pulse oximetry. The decreases in the displayed SpO2 will depend upon the oxygen saturation and relative contribution of these components. The Massimo Cooperation develops an innovative pulse oximetry model called signal extraction. This model accounts for salutation values contributed by the true arterial signal, and by one or more motion or noise signals. It is assumed that under conditions of motion, the detected IR and red signals comprise both the arterial saturation signal and a venous motion noise signal. Massimo pulse oximetry model explains by these two equations, where IR is the pulsatile infrared signal, ρ is the pulsatile red signal, S is the IR signal vector from pulsatile arterial blood, M is the IR motion signal vector generated by venous pulsatile. Ra is the optical density ratio corresponding to arterial saturation. RV is the optical density ratio corresponding to venous saturation. This approach is determining the SpO2 does not depend upon calculating the ratio of red to IR light. This model compute a reference signal using the equations, which is then used by an adaptive filter and discrete saturation transform to identify the correct arterial saturation. In detail, initially the model collect the red and IR signal, then calculate the reference signal for a trial saturation value, followed by send the IR signal and reference signal to the adaptive filter, then adaptive filter removes frequency content in the common between the IR and reference signal. Repeat the process for the full range of saturation value. Then identify the DSP power peak which corresponds to the SpO2. Thank you for watching. See you soon with another interesting topic. Stay tuned.